All right. Very good. Let's move on to our second page. I know, again, this is a lot thrown in a section at once. So we're going to go right here using a chart this time versus a graph, but it seems to be the same thing, okay? So I'm going to look at f of g of negative 1. Now remember, that's f of g of negative 1. So we need to make sure that we look at negative 1 on the g function first. Well, in this chart, here's negative 1 for my x. Where is it on the g? It is at 0. So that means I now get f of 0. And when I look for x equaling 0 on the f function, that gives me 3. So again, knowing how to work it, it's not hard. It's just making sure you know the order in which things are done. All right, so I'm going to change, I'm going to change this part, sorry. Yours probably will be an F there, but mine, I forgot to change it before I copied over here. So we're going to have f of g of f of negative 2. So that means I need to go to the negative 2 onto the f function. Negative 2 on the f function gives me a 0. So now I get f of g of this whole thing comes out, makes that a 0. And then I need to go to 0 on the g function is negative 2. So now I need to figure out what is f of negative 2. And when I take x equaling negative 2 down on the f function, that gives me a value of 0. So those should go pretty quickly. Again, making sure you know the correct order. All right, let's do a composition and some evaluation of these functions. Here's my f function, here's my g function. The first two are just some evaluating with expressions. Then the next two are compositions. So what happens if I have 3b plus 1 and I want to put that into my f function, which is right there? That means that I need to take out an x and put in a 3b plus 1. Well, that rule tells me to square it and then subtract that 3b plus 1. So here again, this is one of those problems that you have a quantity squared that you do not want to write 9b squared plus 1. You're missing a middle term. So let's see if we can practice using the pattern. I'm going to square the first, which gives me a 9b squared. Square both of them. Then I'm going to multiply these two and double. So 3b times 1 is 3b. Double gives me a 6b, and it is a positive 6b. Then I'm going to square the last. So again, that's square the first, multiply together and double, square the last. Now, here, this is a small little distribution where I need to go minus 3b minus 1. Watch those negatives. Okay. Now, we have a 2 out front, so I'm going to distribute that to 18b squared plus 12b plus 2 minus 3b minus 1. And we're going to, whoops, let's see here, I forgot a b. And we're going to combine like terms, 18b squared. This gives me a plus 9b, and this gives me a plus 1. So 18b squared plus 9b plus 1 would be my final answer there. Then I'm going to go to the next example. I need to take 1 over x, and wherever I see an x in my g function, I need to place that. So evaluating g of 1 over x means I'm going to take 1 over x. Now, this is a case where I'm dividing a fraction. So as a nice review of dividing fractions, I'm going to take this guy, and I'm going to, let me undo that, multiply by the reciprocal. So when you divide fractions, you keep the first, then you want to multiply them by the reciprocal of the second. So when I flip that and multiply, then I just get an x as my final answer. Now, f of g of x, here we go. We're going to plug in g of x into the f function, okay? So that means if I want to do that, I replace g of x. What is g of x? Well, it's written up there as 1 over x. So that means now this is what I have to put in to every x that I see in the f function. So that means I have 2 times 1 over x quantity squared minus 1 over x, and now I have to simplify that. So in order to simplify those, you need to make sure you can put them together. We have to have common denominators when we're working with fractions. Now, if I square this 1 over x, square the first, or the top, and square the bottom, I get 1 over x squared. So I have 2 times 1 over x squared, put that over 1, multiply straight across, and I get a 2 over x squared. Nothing I can do with that 1 over x, so I'm just going to rewrite it. but I can now get a common denominator. So here's an x squared, there's an x. They're the same factor, there's just 2 here. So you need to make sure that you account for 1 more over here so I can get that common denominator. So really I get 2 over x squared minus, not 1, but x over x squared. And so we're going to keep the bottom and change the top. So keeping the bottom gives me an x squared. Changing the top, 2 minus x, that's the best I can write it. So 2 minus x all over x squared would be our final answer there. Again, a lot of algebra stuff here possibly for you, so making sure that you go back and review those things. All right, our last one on this one with compositions, I need to take the f function into the g function. So this means I need to look at what is g of 2x squared minus x. Well, some functions are nicer than others. Here, when I want to plug this expression into the g function, I'm going to take out that x and put this in. Then my final answer is just going to be 1 all over that 2x squared minus x. Can't do anything else with that, really. So that's going to be your final answer. Okay. All right. Very, very, very good. All right. Here's a twist to compositions. And then we will go into looking at some slopes and difference quotients and stuff when evaluating, which will help us when we get to derivatives. We're going to identify possible choices for the inner and outer functions of the following composite functions, given that the domain of, give the domain of the composite function. So that means if I define this h of x as f of g of x, I need to determine what is a function that I could have placed, call it g, into the f function to create what I have here for h of x. So I want you to kind of focus in on the expressions. When you have a problem like this, focus in on the expressions and let that expression be the inner function, okay? So like if I have this 4x minus x squared and I've placed it underneath that radical, that would mean that I could constitute g of x, let that be the expression, and then f of x, we're going to take that expression out and put back in an x. Before we took the x out and put in the expression. Now I'm going to go reverse. Take the expression out and put in an x so I get the square root of x. So if you think about this 4x minus x squared, when I plug it in for x, I get exactly what I have here. Now, to figure out what is the domain of that function, you can look at either one of these. You can look at the h if you wanted to. And so recall with a radical, we want to make sure that that 4x minus x squared is greater than or equal to 0. And anytime we have an inequality like this, we must factor. So I'm going to take out an x, be left with 4 minus x. As before, just wanted to show you this again as a reminder. What makes this guy 0 would be a positive 4. What would make this guy 0 would be a 0. Now, I didn't constitute it or say it before, but if you have a quadratic with no double roots, that means there's not a power of 2, not a power of 2. Each one of these regions will alternate. So you really technically only have to check one and then figure out the rest, if that is the case. So I'm going to pick like negative 2. Negative 2 is in this region. When I put negative 2 in here, it's negative. When I put negative 2 in here, that becomes a positive. So 4 plus 6 gives me a positive. So therefore, a negative times a positive is a negative. Now, no double roots. Therefore, I can alternate each one of these sections as a minus plus minus. And so, what section or sections do I want? I want the ones greater than or equal to 0, which is this guy right here. Therefore, my domain, including 0 and 4, would be from 0 to 4, including with those brackets. Okay? All right, very good. Now, what would be our f and g for our next example? Again, hone in on that expression. That is so easy whenever you're given possibilities for that to occur. So if I let the g function be the expression x squared minus 1, then what did I put that into? Well, I'm going to take everything else, take out the expression, and put in an x. That would constitute a 2 over x cubed. And that right there would be a possibility for f and g given h. Now, the last part is I need to find what the domain is of that rational function. And as you recall, the denominator cannot equal 0. So let's find out where it is equal to 0 and take them out. Or you could set it up like this. When is x squared minus 1 not equal to 0? We don't even really care about the cube. Okay, all you got to worry about is the expression. So again, I'm going to factor x minus 1 and an x plus 1. What is that not equal to 0? Well, what would it be that it was equal to 0? Well, this one would give me a positive 1, minus 1 gives me 0, and negative 1 plus 1 gives me 0. Therefore, x cannot equal negative 1 and positive 1. So you can write it like that for the domain as well. There would be the domain of that one. Okay? All right, very good. All right, moving into the last section here, dealing with some symmetry. Okay, actually not dealing with symmetry. We've got a couple more little things to do, my bad. We need to talk about this difference quotient that will come up in derivatives, and then we'll talk about symmetry. So, you will see shortly why the slopes of lines and curves are crucial to the fundamental ideas of calculus. Now, let's review some things about slope. Now, a line given, if it goes through any 2 points, is what we refer to as a secant line. Okay? All right, now, if I have 2 points, here's my graph, okay? I'm going to call this point P, call this point Q, and I need to, I'm going to say this is X, and if I add some distance to that, then I'm going to say that this is X plus some distance H. Now, if I were to plug this into my y equals f of x function, when I kick that out, that means that this is the value of f of x, because I plug that into f and it kicks out f of x. And when I plug this into f, then over here, this is going to kick out f of x plus h, because I put in x plus h and kick out my function value. Okay? Now, if I want to find out what the slope of the secant line is, that means I have to figure out what is the rise over the run. Okay, now let me draw that secant line. I don't have that on there. So the secant line would be this guy that goes through those 2 points, okay? Now, what is the secant line? The secant line, the slope of the secant line, this, if you want to write that point, that is the point x plus h comma f of x plus h. This is the point x comma f of x when we do xy points. So to find the slope, we need to take y minus y over x minus x. So that means I need to take f of x plus h minus f of x. So to find this rise that I have right here, you take the difference between each one of those. So here's the rise right here, another little delay. Then I need to take the difference in the x values, which would constitute along here. And I would take the x plus h minus the x, just to be consistent. And notice in the bottom, I could cancel out an x. Therefore, we have f of x plus h minus f of x all over h. And that right there, that expression is going to be very, very important later on. Okay, so, again, we have a delay. This f of x plus h minus f of x all over h is what we know, or is known in calculus as the difference quotient, and can be expressed in several different ways depending on how many points there are labeled. For example, if I have a comma f of a and q is x comma f of x, we can also express between those 2 points. Obviously, since it is 2 different points, we can go y minus y over x minus x. So I could say f of x minus f of a all over x minus a is another version of that difference quotient. And what we interpret this slope as, this is the form of the average velocity, whoops, sorry, not average velocity, it should be average rate of change. Average rate of change. Let me... which, in section 2.1, you're going to see it as the average velocity. So that is going to be the average rate of change of our function f over an interval. Well, what are we talking about? We're on the x values from a to x, so on the interval a to x. Close that off. Okay? All right, page 4. Let's do this and evaluate some functions. So, evaluating the function here of this difference quotient with that 2x squared minus x, which we already saw that before. So, we're going to take x plus h and plug that in there. So, what I get is 2 times x plus h squared minus x plus h. So this right here is all of that f of x plus h. Then I'm going to subtract f of x, which is that whole thing, 2x squared minus x, all over h. Now we have to simplify that. Okay, so if I'm going to simplify that, then we are going to square each one of those first. So I'm going to take this and do the pattern. So I'm going to have 2 square the first, multiply the 2 and double gives me a 2xh, and square the last gives me an h squared. Then we have our minus x minus h. You want to be very, very meticulous here because there's a lot of places that there could be some mistakes. Then I'm going to go ahead and distribute that negative on top, which becomes a minus 2x squared plus x all over an h. Now I'm going to continue over here because I still need to distribute that 2 first. 2x squared plus a 4xh plus a 2h squared minus the x minus the h minus the 2x squared plus x all over h. So it does take a lot to write it out sometimes, so please make sure that you do so. Alright, so I'm going to cancel anything that I can. Notice I have a 2x squared and a 2x squared that can be gone. I've got this that can be gone right there. And I also have an h that I could factor out, but I'm going to think of it like this, that when you have a rational function, that you end up having all these h's in common along the way. See, I can't combine this with this because this guy over here doesn't have an x. This is supposed to be just an h. And so each one of those have an h that I can cancel, cancel, cancel. You must cancel with every single one or with none at all. So when I cancel an h with everything, I get a 4x plus a 2h and then a minus 1. And that right there is the expression that I want to have for that difference quotient for that function. Okay? All right, now let's do the other version. The average rate of change for that difference quotient for x cubed, okay? So that means here I have f of x, which is this guy, x cubed, minus plug in a, which gives me an a cubed, all over an x minus a. And I have to simplify that. Well, this kind of goes back to what we have whenever we are factoring. So being able to factor a difference of cubes is going to be very, very important. Okay, so one thing that you have is another pattern with a difference of cubes, okay? So a difference of cubes, instead of it being a difference of squares, we have perfect cubes here now, is actually factored into a binomial times a trinomial. Now, when I teach this in Algebra 2 or college algebra, this is what I normally do. The signs of this binomial and this trinomial are constituted by what we say SOAP. So same, opposite, always, positive. So this has to be the same sign, this is the opposite sign, and this is always positive. What do I cube to get an x cubed? It is an x. What do I cube to get an a cubed? It is an a. So that's what goes in our binomial. And then here comes a pattern for this trinomial that is very similar to what we just did up here with this quantity squared, except for I take away the double. So I'm going to square the first. I'm going to just multiply these two together to get an xa. And then I'm going to square the last. So again, it's just like that pattern of a binomial square, except for you do not double. All over an x minus a. So notice now that I've factored that difference of cubes, this is going to cancel out that binomial, leaving me with x squared plus xa plus a squared as my final answer. So again, those are going to be very, very important. You want to make sure you practice those. Get enough paper. Don't try to squeeze it down. Don't try to do it all in your head. Make sure that you write it all out. All right, our last one here. With symmetry, I know this is a really long cast, but again, there's a lot of information in here in section 1. The word symmetry has many meanings in mathematics. Here we consider symmetries of graphs and the relations they represent. So take advantage of symmetry. Often saves time and leads to insight. Now, a graph is symmetric with respect to the y-axis if, whenever the points x, y is on the graph, then the point negative x, y is also on that graph. And this property means that the graph is, unchanged when reflected across the y-axis. Now, a graph is symmetric in respect to the x-axis if, whenever the point x, y is on the graph, then the point x negative y is also on that graph. And this property means that the graph is unchanged when reflected across the x-axis as well. So notice for y-axis symmetry, it is a negative x. For x-axis symmetry, it's a negative y. And when we talk about having symmetry with respect to the origin, then if we have the point x, y on the graph, then negative x, negative y is also on the graph. Now, symmetry about both x and y axis implies symmetry about the origin, but not vice versa, okay? So let's look at some examples, and then we'll do it mathematically of how this kind of coincides with even and odd functions. So if I have y-axis symmetry, kind of the most famous one is your y equals x squared. So this parabola would be symmetric to the y-axis, because if this is the point xy, then this is the point over here, which is negative xy. So that would be an example. To have x-axis symmetry would be kind of a sideways parabola, would be an example. If that's the point xy, then this is the point x negative y. That actually would not be a function because it would not pass the vertical line test. And an idea of a symmetry could be something that looks like this. Let me undo that because I want to go through the origin. Because that's important if we're symmetric to the origin. Alright, so we have something like this. So if this is the point xy, then this over here is going to be the point negative x, negative y as well. Okay? Alright, very good. Now, symmetry in our functions as it corresponds with even and oddness. So again, a review of even and odd, not that we do that too much, but it's important when we're working in some of our graphs. So if we have an even function, then it means that the property where I evaluate at negative x kicks back the original function f of x for every x in the domain. And the graph of any even function is symmetric around the y-axis. So like x squared is an even function because we end up having symmetry over the y-axis. If I look at an odd function, it has the property that when I evaluate at negative x, so you have to figure out what this is to work with even and oddness, or actually just look at their graph. Then you have negative of the original function for every x in the domain, and the graph of any odd function is symmetric to the origin. Okay, which is very, very important to remember. Those two things go hand in hand. So here's our last three examples of this section, marathon section that we have here. We want to identify symmetry, if any. So let's go ahead and just kind of identify with figuring out what is f of negative x, okay? So when we have a function, the easiest way is to evaluate f of negative x to see what you have. And so notice here that when I take negative x to the fourth, that just kicks out a positive x to the fourth. Whoops, that should be a squared. So when I do this squared, that gives me a positive x squared times a negative 2, still is a negative 2x squared, minus 20. And if I look at what that is to the original function, that is exactly the same. Therefore, this is f of x. So then this constitutes that we have an even function, which means that we are symmetric to the y-axis. Now, if I look at g of negative x, then I'm going to throw negative x and cube it, minus 3 times negative x plus 1. So when I do the negative x cubed, I get a negative x cubed without parentheses. This would end up changing the sign to a positive 3x plus 1. But if I try to take that negative out to match up with my original, and I change the sign on all three of those terms, notice that this is not exactly the same as what I started with. Therefore, this is not equal to the opposite of g of x. Therefore, this constitutes a neither on my even and oddness, and it would not be symmetric over the y-axis, the x-axis, or the origin. Okay? All right, and last one, let's look at h of negative x. This ends up giving me 1 over negative x cubed minus negative x. And when I simplify that, I get 1 over negative x cubed plus x. But then when I factor out a negative, I get 1 over negative x cubed minus x. And for a rational function, whether or not I have that negative down below or up top or completely out front, I can kind of move it into whichever area that I want. Oops, that should be an h. So notice I do actually get the opposite of the original h of x. Therefore, this is an odd function, which constitutes symmetry over the origin. And that, ladies and gentlemen, is the long first section of our calculus class. I know that that's going to be trying on some of us, but we can definitely hopefully get those reviews all in sync so that we're raring to go when we actually get into our calculus. So, like I said, the next section we're going to do a lot of graph transformations so that we can start talking and do a little bit more with our functions and get into our calculus, the meat of what our class is about. So, until next time.